Okay, let's get started. So we've set, the office hours are set. And so if you go here, there's right below lecture videos on Blackboard, there's a link called office hours. So if you ever forget, that's the place to go to find out exactly when office hours are. Let's review those. Because we'll be collecting the written homework on Wednesdays, we just front-loaded all the office hours Mondays and Tuesdays. If you need to see us, if you need help Wednesday, Thursday, or Friday, don't hesitate to email us or make an appointment. Okay? You can still do that. You can still get help. But we just wanted to make our general office hours so that you get started on the homework over the weekend, and then you'll be ready to bring your questions. And so for most of you, you're going to need office hours. We can't do everything in lecture and in recitation. There's just too much to do. So we're going to give you the most important things, and then some of the stuff on the homework you're going to have to transfer and extend and bring things together that maybe we didn't do exactly in class. So that you're going to need to come to office hours to work that stuff out. All right, so Ben, if you have recitation on Wednesday or Friday, Ben is your recitation leader. Mondays, he's 11 to 1, and Wexler 303. Wexler is also PSA. It's the old PSA building, so it's the Physical Science Wing A. But it's now called Wexler. Okay, so I'll be 1 to 3. ECA 209 is right there across from the bookstore. Manevsha, is she here? Is Ben here? Okay. 4:30 to 6 on both Monday and Tuesday, and Wexler 303. Okay? So, and then Tuesday, I'm not going to read this to you, obviously. So these are the office hours. You guys come get help. Come get help. Take your pick. Come to more than one. Make appointments on other days if you need to, or email us questions. Okay, any questions about office hours? Going to be an important element of the course for your success. We are your allies, so come get the support that you need. Okay, so let's, and then so the homework. I will, this afternoon, I'm going to, there'll be a part C and a part D. I will finish that up. It'll be finalized this afternoon. Hopefully you've started by now. If not, you definitely want to start this weekend, okay? It's a week's worth of homework. It's going to seem like a lot, but it's a whole week's worth of homework, okay? So it's the right amount. You've got to discipline yourself to spread it out and work on little bits either, every other day or every day, okay? Questions about that? So again, on C Friday afternoon, this will C and D be finalized. Any questions before we? Yes, please.
So, like in the homework, I noticed that there was like a few questions that were just to be done in GC.
Yeah.
So, like, is there a way that we should be documenting that?
Yeah. So you can print. So once you do your GC files, print out the files. Yeah. There's a print. You could take screenshots, but it's probably easier. Actually, print out the GC file and then turn that in with your homework, and that will show both the command lines and any graphs if you have graphs. Okay. Oh, so I will say yes. Any homework that's from the book, you're gonna do that on your own paper. There's not, do all those solutions on your own paper, and then for normally when I do handouts like this, I leave space, and you've got graphs in this one that the intention is that you're sketching and doing things on the graphs, axes that are given. That's going to make it the easiest. So for this insect population worksheet, go ahead and print that out and put all your responses on your printouts. Okay? Any other questions about the homework? Okay. So we will not see you Monday. We'll not see you Monday. This is the last class before we see you next Wednesday. So that means Tuesday, you've got the chance for all those office hours on Tuesday, but not on Monday. And then in future weeks, you'll have Monday and Tuesday. Okay. So we were working on the soldier lowering the flag. And what kind of function was this on the left? Okay, is this approximate or exact rate of change? Approximate. She said approximate. Agree with that? Now, this is our exact rate of change function for the soldier as he's pulling on the rope in kind of one hand over hand, right? In between hands, the rate kind of goes to 0, and then as he's pulling, the rate is this like about this constant of negative 0.75. Okay? And what did we say? We said we wanted to, our endeavor was, what? You know how fast something is changing at every moment? Exact rate of change? You want to know? Okay, so maybe my TAs, can you just circle around and make sure people are off phones and computers, paying attention? Just watch for that. Okay, so we know how fast something is changing every moment. We want to know how much we have. So if this is the rate of change of height, then what is how much we have? What would that be like? Yeah, so like either change in height or height. Those are both kind of the idea of how much you have, either the height of the flag or change in height. Okay, and so we sketched, based on this rate of change function, we made a rough sketch of what we thought the change in height would be starting at 0.6 seconds, and we came up with something like this. Can you see it? It's real faint, but so it's the change in height is it's accumulating. That's negative change in height because the height's lowering, and then in between hands, there's not very much accumulation, so that flattens out in between, right? So we said our goal is to write a function like that. We want to write a definition, create the definition of the function like that. And we said this is hard because we have a changing rate of change, right? Changing rate of change makes this difficult. We know if we have constant rate of change, that math is pretty easy, right? The math to get bits of accumulation from a constant rate is pretty easy. So we want to take advantage of that. So what did we do? We made a new rate function, right? An approximate rate function. And we said changes in x were 0.35, starting at 0.6 seconds. And we said one way to make that approximate rate function would be take the exact rate of change at the left side of each interval, and then let that be the constant rate for that whole interval until we get to the new interval. And then now take that actual rate of change at the left side and make that the rate of change, constant rate of change for the whole interval. So do you see how this is generating that we call the pretend rate function, right? A pretend rate function. And based on that pretend rate function, we made a table, right? We made a table and we came up with the corresponding pretend accumulation function, which is not exact, right? It's not matching what we know to be the exact accumulation function, but it's doing okay, right? It's got the general trend. But we want to get that thing exactly, right? We want to get that light gray graph, the exact accumulation, we want to get that exactly. So we said, how could we do better? So where we left off last time. How could we get a pretend rate function and then a pretend approximation function? How could we do better? More smaller intervals. Every time we make the intervals smaller and take more of them. So I want you to look on the right graph when I do this. Watch the right graph. So do you see, let's just pause it here. So you see how the pink one, that's based on the blue approximate rate function is our pink one. It's trying to be like the actual, but it's not doing a great job. Now I want you to keep your eye on the pink one. I'm going to make the interval smaller and take more intervals and watch what happens. Better? Yeah, right? Better. And then looking at the approximate rate function, taking more smaller intervals, it's doing a better job pretending to be the actual rate function. Okay? So then this is kind of gives us the idea of how we can get then the exact accumulation function. How are we going to get the exact accumulation function? If making the intervals smaller and taking more of them makes it better, then what's the road to exact accumulation? Okay, so we really can't do that because a point doesn't have any interval. Because we need dy equals m dx. We still need some change in x. So we can't take it pointwise. But what's the next best thing? Yeah. Really, really small, right? Really, really small intervals. super small intervals. So like here's an example, 0.005. 0.005. Now I'm going to turn off the right here. So look at the rate function. Is it approximate or exact? Do you see what that is? What those little dots are? There's still little intervals of constant rates. It's not doing, sometimes it shows vertically, so it's not doing great. But the idea is, let's do that better here. Watch. I can do that better here. There we go. So there's still little teeny intervals of constant rates, right? Constant rates, but when you look at it, it's virtually, now when you look at it, it's virtually indistinguishable from the true rate function, right? So it's still made up of constant rates, but just in such small intervals, 0.005, that when you look at it, it's like you can't tell the difference, right? You can't tell the difference. And then what about the approximate accumulation function? You can't tell the difference, right? So this is the key to getting exact accumulation. We're going to make the interval so small that we can't tell the difference. That we can't tell the difference between approximate and exact. And then we'll call it a day. We'll say that's it. Since we can't tell the difference, or we have to take things out to 50 decimal places to see the difference, right? Say it's close enough. Close enough so that we can't tell the difference, and we'll call that the exact accumulation. So that's our roadmap of, you know how fast something is changing at every moment, and you want to know how much of it you have at every moment. What's the first function we start with? Exact or approximate rate or accumulation. We start with? Which one? Exact rate. And from that, we build what? From exact rate, we build pretend rate, approximate rate. And from the approximate rate, we can get, now we've got constant rates, so we can get approximate accumulation. And then from approximate accumulation, we make the intervals really small, we get exact accumulation. That's the progression. And then that accumulation could be net accumulation, like this, right? Tracking changes, or total accumulation, right? How would we get total accumulation from the net accumulation? Just one simple step. We need the initial height, right? And we would just add the initial height to all those changes in height, and it would give us the height profile, right? So if the initial height was 10 meters, then by just adding 10 meters to all these y values, basically moving the graph up 10 meters, now we'd have the height graph instead of the change in height graph. So that's the difference between net accumulation and total accumulation. Okay, so actually, I need your guys' help to pass these out. So I have a new scenario here. So we're going to kind of practice all of that again with a new scenario while I take attendance. Okay, so here's a new situation. And so this is unloading sand onto a scale. Unloading sand onto a scale. Okay, this is the rate of change of weight as a function of time. And that rate of change is in hundreds of pounds per second, and then the time is in seconds. So this sheet is going to kind of lead you through kind of a similar example of the discussion we just had, so you can practice. You can work together. Take your time. Make sure you fully understand and answer each question before you move on to the next one. So I've placed the questions in order purposefully so that don't skip over anything and go on to something later. Make sure you understand everything before you go on to the next thing. And then I will, as you're working on it, I'll be taking attendance, and we'll regroup here in about 7 or 10 minutes, see how you do. Okay? Okay, you're either making progress or you're getting help. So get help from someone around you, get help from Ben or Manesha. Here we go. So this is exact rate. And what's our goal? Our goal is exact accumulation, right? Exact accumulation. And what did you get for what our goal is? So we just want to start with a rough sketch what exact accumulation is. You should have gotten something like this. Just as a rough sketch, like that. Without paying attention to any numbers, just by the shape of the way that the rate graph is. And is this total accumulation or net accumulation? Net, right? So it's net. Because why? We don't know how much. There might be some sand on the scale already. So then we're tracking the change, right? We're tracking the change in weight based on this new amount being unloaded, right? Okay, our units are, this is hundreds of pounds per second here. This is hundreds of pounds, and both the x-axis are seconds. Those are your units. So this is, our goal is to write the function that is, or to express the function that is the black one over there. The exact net accumulation. And so, why is this a difficult process? Where do we hit this roadblock, right? So it's talking about buildings. We've got the exact rate function, but it's talking about creating a different rate function. Why do we need to do that? Why do we need to do that? Lots of you asked this question. Why do we need an approximate rate function? Okay, so we've got a continually changing rate of change. What is our key from day one, right? Our key from day one, in order to express or get some amounts of accumulation, what was the key to that? Yep. And so dy is mdx. This is the key principle for getting accumulation from rate. And that depends on, mdx depends on that m is constant, a constant rate of change. This is a continually changing rate. That's where we hit this roadblock, right? We can't work with that because mdx says m needs to be constant for that whole interval of x. But if x is constant, then, and we've got our interval, then we can get a little bit of a change, right? A little bit of accumulation, dy. Okay, so that's why we make this new pretend rate function. And what is that? I told you to use intervals of 0.3. And use the left side. So there's our goal over there on the right. Using the left side, you should have sketched something like this. And as time goes by, think about those points being generated, right? This is a new function. It's a new set of points. Each one of those shelves is a set of points, right, for that interval. Okay? So how do we express those things exactly? So this one right here, this rate, what is this rate right here? Exactly. No, so exactly. So you're just, that's an estimate. That's, you do want to estimate it eventually, but we want to express it exactly. It's not r of 0, because we're creating the r function out of what function? R sub w. So this right here, that rate, which we see on the y-axis, is r sub w of 0. Right? Because it comes from the exact rate at the left side of the first interval. This next one here, it's just a little bit bigger than 1. What rate is that? Exactly. R sub W of 0.3. You don't want to put it over here because it's a value, it's a rate that's really a rate that's represented on the y-axis. So that's why I'm putting it over here on the y-axis. Okay, this one is just below 3. Just below 3. What is that rate? R sub W of 0.6. Yeah, you have the right idea. I just skipped ahead one. Yeah. Okay, so function notation, right? It's been working on in recitation. We're going to see it all semester. Super important that you can represent values with function notation. So this the R function, which I'm showing sketched here in blue, is comprised of these values. First, R sub W of 0 for the first 0.3 seconds. Then R sub W of 0.3 for the next 0.3 seconds. And then R sub W of 0.6 for the next 0.3 seconds, etc. Okay, so that's the, and then you can estimate those, like I was saying, like someone said about 0.25, and then I said a little bit less than 1, or a little bit less than 100 pounds per second. And then this one, a little bit, somewhere, it's close to 3, right? Close to 3, something around 3. A little bit less. Okay, questions on that? Okay, and so then, based on that, so does 5 make sense? Does number 5 make sense then? The exact, represented exactly means taking values of R sub W. And those values of R sub W then comprise our approximate rate function R. Okay, so then we want to write what A of 0.8 is. So A is our approximate accumulation based on the blue approximate rate function. So how would we write the net accumulation up to 0.8 seconds based on R? So R sub W is 0 times 0.3. So that's what? So that's the amount of accumulation in the first interval. M dx plus? Right? Times 0.3 again. That's the little amount of accumulation in the second interval. Then what? So W 0.6 times 0.3, right? Oh, it's different. So this isn't a full delta x interval, right? It's not a complete delta x interval. We only go partially into that interval, starting at 0.6 up to 0.8, not all the way to 0.9. Do you see? So it'd be R sub W 0.3 times 0.2. Does everyone see that? 6. Yeah, thank you. I was just checking you guys. And yes, please, if you see a mistake, or even if you just think it's a mistake, raise your hand so we don't, please, I will make mistakes. So please raise your hand and say, is that right? And then we'll make sure it's right so we don't waste time, okay? Okay, does this make sense? So this is how we would, now, we got to think about it. So this really is our, when we're looking at these rates, these are really our R function, right? This is using the R function, but I'm expressing that in terms of the R sub W function. So when you think about this, you want to think about, oh, this is, I'm using my R, my approximate rate function, to calculate this amount of accumulation up to 0.8. Yes, sir?
So the approximate rates that we did, that's a brand new function.
The blue one.
Yes.
That blue function is a brand new function. It's the pretend rate function based on the exact rate function. And we defined it, we built it from those exact rates on the exact rate function. And so that blue one is a new, you're looking at two different functions on that left graph, right? You're looking at the exact rate and the approximate pretend rate. Okay, so the reason I asked this next one was, so suppose now the interval is 0.13 or 0.013. What would this be like now finding A of 0.8? So there's like a pattern to this, right? We're going to add up all the accumulation from what we call completed intervals. plus. We've got a little more accumulation, what we call the current interval. So where the current value of x is in some interval, and we call that the current interval. So we get all this sum of accumulation from completed intervals, and for every one of those, the interval width is a full delta x, right? And then there's a little bit more accumulation from what we call the current interval, which is where x is currently, right? Somewhere in the current interval. So because these all look alike, right? These all look alike, and we're making a big sum, that's why we use to make this easier, we're going to use a sum. So instead of writing, so it was 0.13, you'd have to write a whole bunch of these, right? You see that if it's 0.13, you'd have to write, I don't know, 10 or 12 of these all out. Since they all look the same, they're all a rate times the same delta x, we can just do it this way. We can say r x, say for the ith interval, times delta x. And so we're going to let I start at 1 for the first interval and go up to what? The number of completed intervals. So that sigma just means sum up a bunch of these things. Rate times delta x plus rate times delta x plus rate times delta x for all those completed intervals, which is a lot easier to write than trying to write it out if there's 10 or 20 or 50 or 100 or 1,000 of them. We'll just, since they all look alike, they're all the rate times delta x. We're just going to sum a bunch of those up. And then we'll have the rate of the current interval times, so the amount of change in the current interval is what it was at our dx. Remember we said dx is variable, right? Dx is variable. So imagine x changing through the current interval, then dx is increasing starting from 0 in that current interval. So that's the amount of change in the current interval. Okay, so we're getting close. We're getting close to this being able to, again, what's our goal? Write this. And we're getting close to being able to do that. Question? No, I'm just talking about like, so first interval, I means the interval number. It's not a value. So I is the interval number. So first interval, second interval, third interval. That's what I'm using I for. To mean what number interval it is. So it'll start at 1. First interval, second interval. Is that okay? Okay. Again, check Blackboard. Get going on the homework before Tuesday.